Just please, if you don't mind, if you can mute the mic.
Yep, I'll do that.
Thank you very much. Thank you. Hala, do you hear me now? Okay, back to the presentation. So this is recorded, and you will have it later on. I'll share it with you in the same Teams chat related to this call. Anyways, so back to the topic. Again, this is very important for you to understand the context of MMin, MMax, and it can be useful for you also in your day-to-day work. So a few informations. First of all, calibration and why is it important for what I'm talking about. Now, calibration, as you may already know, is simply a way for you to convert one unit into another unit. For example, if I want to do D-dimer, D-dimer is a photometric assay, meaning the analyzer measures optical density. But of course, you don't report your reclination optical density. You report D-dimer in microgram per ml or etc., whatever it is. Okay. Fibrinogen, for example, fibrinogen is a clotting assay, but I report it as milligram per deciliter, which is concentration. So the calibration allows me to convert for fibrinogen, for example, seconds into milligram per deciliter. So again, calibration is simply a way for you to convert one unit into another using a formula, using a curve, these things that you already know. We will not dive that deep into this concept, but the idea is for you to know that calibration is for you to convert one unit into another unit, okay? Now, our analyzers, they do two types of measurement, okay? The first one is the clotting tests, which is in seconds, as you know. The second one is photometric assays or photometric tests, which are measured in optical density. So the analyzer gives me an output in seconds and in optical density, okay? Seconds, I can sometimes report it as it is, but in many other cases, like in factor assays, seconds are meaningless to me. I need to report factors, for example, in percentage or IU per ml. Okay, so I need a calibration curve for these assays where I convert the second into something different. For photometric assays, optical density is never useful for me clinically. So I always have to convert optical density into something different. So for photometric assays, I always need a calibration because optical density is absolutely meaningless to me. Okay. So when I talk about raw measurement means the value that the analyzer measures, okay, that I later on will convert into something different in most of the cases. Okay, but raw measurement, for example, can be seconds, as we said. PT can be reported in seconds, APTT can be reported in seconds, okay? So clotting tests can be reported as raw measurement in seconds or as converted values like percentage, IU per ml, etc., 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 which requires calibration. Now, imagine that this line, the horizontal line, represents your calibration curve, for example, okay? And let's say the calibration curve lowest value or lowest measured value was 0.2 optical density. And the highest measured value in my calibration that I measured through my calibration was 0.8 optical density. Again, my calibration curve is this line, okay? The highest measured value through my calibration was 0.8 optical density. The lowest measured value was 0.2 optical density. So basically, I'm telling my analyzer, okay, draw a line here, and anything between 0.2 and 0.8 optical density, okay, I can easily apply it to the line, and then I can measure concentration from it. Let's say, for example, again, D-dimer. If I got 0.4 optical density for D-dimer, let's say, for example, it correlates with 2 microgram, for example, okay? Now, if I have optical density less than 0.1 or higher than 0.8 optical density, I simply did not give the analyzer any instructions on what to do higher than 0.8 optical density or lower than 0.2 optical density. So if the analyzer obtains these values, let's say 0.1 optical density, it simply thinks that, okay, you did not give me a curve that covers this range, so I cannot do anything with it. In this case, it will give you an error. I'll come to explain later on the details, but just to give you the concept. However, I can do something that will allow me to extend my calibration curve outside of my actual calibration runs. So this thing is called extrapolation. Okay. Extrapolation simply allows you to extend your calibration curve theoretically into infinity. Okay. So whatever optical density value, whatever second value you get, okay, you can get a concentration out of this raw measurement value. However, extrapolation is only applicable to linear and hyperbolic formulas or calibration curves. Now, you would probably think, oh, we came into these details now. You don't have to memorize or remember a single thing, or basically analyze anything to find linear or hyperbolic. You simply go to your SOP or you go to your methodology and go to the calibration section. It will tell you this calibration is linear or hyperbolic. That's it. You don't have to memorize a single thing. Plus, this information is available in the application version of the MMin and MMax table. It will tell you this methodology, okay, extrapolation is applicable or not. It's linear or it's hyperbolic, okay? So again, extrapolation is only applicable to linear or hyperbolic calibration curves, okay? Some assays, they have second or third order polynomial calibration curves. What does that mean? I don't care. Probably you don't care. We will leave it at that. You can find this information in your calibration section in the methodology. Okay, simple as that. So if my assay has second or third order polynomial calibration curve, extrapolation is not possible. So simply, I cannot extend my calibration curve more than the highest obtained value or the lowest obtained value. So if the analyzer actually got a value outside of my calibration bounds, it will not be able to give you any concentration. Okay, even if you enable extrapolation, still the analyzer cannot extrapolate second or third order polynomial calibration curves. Linear or hyperbolic, such as, for example, antithrombin 3, for example, it's a linear calibration curve. Okay, even if you get an optical density outside of the calibration curve, the analyzer can still give you a concentration based on the extrapolation. However, for example, if you use von Willebrand ristositine, okay, that's a third order polynomial, let's say. If you exceed your calibration limits, the analyzer will tell you, I don't know. Okay, MMin or MMax. I'll explain that in a second. Now, MMin or VMin are exactly the same thing. MMax or VMax are exactly the same thing. Okay, some older software versions still use VMax or VMin. It doesn't matter, just matters that you know that they are exactly the same thing. The name doesn't mean a single thing. Now, when I say MMin, this means your raw measurement is lower than a certain cutoff, which I'll explain to you in a second. When I say MMax, means your raw measurement, second or optical density is higher than a certain cutoff. So for example, for clotting assays, when I say MMin means that my clotting time in seconds is lower than the minimum time defined in the test setup or lower than the lowest clotting time in the calibration if extrapolation is not applicable. MMax or Vmax for clotting assay, for example, means that my raw measurement in seconds is higher than the max time defined in the methodology or higher than the highest calibration value in my calibration curve if extrapolation is not applicable. You will see that in a second in an easier way. Optical density, the same applies. So for MMin in an optical, in a photometric assays, okay, the raw measurement in optical density is lower than 0, which of course is not possible, or lower than the lowest point in my calibration curve. Okay, MMax or Vmax means also your optical density is higher than 2.5. The analyzer cannot measure optical density more than 2.5, by the way. It's physically not possible for the analyzer. So OD is higher than 2.5, or if extrapolation is not possible, the highest calibration point. Okay, now, if you remember yesterday, I sent you one table that will help you easily understand why VMin or VMax or MMin or MMax are generated, and I will just take you through it very briefly at the moment. Just a second. Okay. Does anyone not see the Excel sheet? I will assume then you all can see it. Okay. So, as you can see, of course, we have clotting assays and we have photometric assays. Fine. Raw measurement for clotting assays is always in second. Raw measurement for photometric assays is always optical density. Calibration required or not required, as explained. Okay, if I want to convert away from the raw measurement, of course, I need the calibration. Okay. The only case where I report the raw measurement as it is when I report the clotting assays in second. That's it. Now, extrapolation is not applicable to clotting assays reported by seconds because we are not converting anything. So what am I extrapolating? There is nothing to extrapolate. Okay, now this is the important part for me. You can see here the type of the calibration curve. Okay, so for a linear or hyperbolic calibration curve, extrapolation is possible. Okay, we said for second or third order polynomial calibration curve, okay, extrapolation is not possible. So here, on or off, extrapolation on or off doesn't make any difference for Vmin or Vmax. You will see. Okay, so now here, for clotting assays, how are MMax and MMin determined? Okay, when I report the raw measurement, then max time and min time in the methodology determine when do I get MMin or MMax. Okay, even if I have a clotting assay, okay, that's linear or hyperbolic where extrapolation is on, my limit will still be max time or minimum time because I can extrapolate outside of my calibration curve. However, if I have a linear or hyperbolic clotting assay and you switch off the extrapolation, the moment you get a value outside of your calibration curve, the analyzer will tell you MMin or MMax. Fine. So for example, imagine you have a factor assay where the lowest point in the calibration curve is 40 seconds. The highest point is 90 seconds. The moment you drop below 40 seconds, you will get MMin if your extrapolation is off. The moment you exceed 90 seconds, you will get MMax if your extrapolation is off. If you switch on extrapolation back on, okay, then you are bound by minimum time or maximum time in the methodology. If you drop below the minimum time, you get MMin. You exceed the maximum time, you get MMax. Okay, and here is a little further explanation. When do exactly you get MMax, and when do you exactly get MMin? Any questions about this curve? About this table, sorry. Is it clear for everyone, this table? If it's not clear for anyone, please stop me and tell me, because it's important to understand that particular bit. So should I assume it's clear for everyone? Okay, then I will assume so. So these slides will just help you visually understand what I have sent you in the table. Okay. So your boundaries, let's say for linear extrapolation, it's on. Okay. Then result for calibrated and null calibrated test are bound by your maximum time or minimum time. You switch off your linear extrapolation. If the assay is calibrated, then you are bound by your lowest calibration point and highest calibration point. If there is no calibration, then extrapolation is meaningless. Extrapolation is applicable to the calibration curve. Okay. If I report PT in seconds or PTT in seconds, then my boundaries are the maximum time and the minimum time. For optical density, okay, if I have a linear or hyperbolic calibration, as a linear extrapolation is applicable, okay? And when it's on, basically my boundaries are 2.5, highest value for optical density, or 0, lowest value for optical density. However, if I switch off my extrapolation, my boundaries, again, they're the lowest raw value in the calibration and the highest raw value in the calibration. Now, the reason I needed to explain to you all of this is that some assays, MMax can mean the concentration of your analyte is very low. For some assays, MMax can mean the concentration of your analyte is very high. So some customers, they think that MMax means your value is very high. But it actually just means that the raw measurement is very high. And the raw measurement sometimes can negatively correlate with your analyte. For example, if you have factor assays, the longer the clotting time, the lower is actually the concentration of your factor. So if a factor assay give you MMax, this means the concentration of the factor is very low. However, the opposite, for example, let's take D-dimer. D-dimer, when you get MMax, this actually means your D-dimer is very high. Okay, so how do I know then when does MMax means very high, when does MMax mean very low, or the opposite for MN? The way to know that is for you to know exactly the principle of the assay. And knowing the principle of the assay is simply not possible for a customer. It's too much information. That's why you will need a table that will easily tell you when you see MMax for this test, then report more than such and such. Now, let me share with you the table that I've shared with you already, or I put it on the screen to explain how it works. Just a second. Okay, so this is the customer version. So let's say the customer is running factor 8 assay, for example, okay? So we have factor 8 assay, and they're using the immunodiff line. Let's assume they're using the immunodiff line, okay? So I'm using factor 8 assay, and I got MMax. What does MMax mean? Means my time is more than 200 seconds. The customer doesn't care about this. The customer wants to understand what is the interpretation of MMax. So the interpretation of MMax means your factor concentration is less than 0.7. Or the customer obtained MMin. The customer says, okay, how do I find what does this MMin mean for factor 8? So we are in factor 8, immunodiff, yes. All right, MMin means your clotting time is less than 20 seconds. The customer says, I don't care about this. How do I report to my patient? Then interpretation of minimum means your patient has more than 400% factor 8 concentration. Okay, let's take another example. Let's say I have liquid antitin A, low molecular weight heparin. Okay, I think this is the old table. Just a second. My apologies. Okay, back to this. So again, we were talking about liquid antitin A, low molecular weight heparin. Okay, the customer tells you, how do I interpret my MMin MMax? So the red or the pink is MMax. Okay, the blue is MMin. So liquid antitin A, low molecular weight heparin. The customer says, okay, I got MMax. This means the heparin in my customer's blood and my patient's blood is too high. This is absolutely wrong. MMax for antitin A, for example, means heparin is very low. It's below 0.1. Okay, so if you report to the clinician that the heparin, low molecular weight heparin in the blood is more than 2.0, they will stop the anticoagulant treatment for this patient. And this can mean that this patient will thrombose. So incorrect interpretation for MMax and MMin can be actually very critical for the patient. Okay, that's why I wanted to have this session with you to make sure that everything is clear and understood. Now, there is this sheet that is actually for you. That's why, of course, it's labeled for application specialist. The point of it is to highlight for you how the assay itself works. For example, if we go to the antitin A assay, okay? It's photometric assay, the raw measurement is optical density, the units, we have different units because we're measuring different things, rivaroxaban, apixaban, UFH, low molecular weight heparin. Now, MMax interpretation means that we have low anticoagulant concentration. MMin interpretation means we have high anticoagulant concentration. Now, why is that? Because the calibration curve, okay, is negatively correlated, meaning the optical density is negatively correlated with the concentration of your anticoagulant, meaning the higher the optical density, the lower the concentration of the anticoagulant in the blood. Okay? That's why the higher the optical density, you will get MMax. And MMax means you have a very low concentration of your analyte, which is the anticoagulant, basically. Calibration curve type, linear, hyperbolic, third order, second order, polynomial, doesn't matter. Extrapolation applicable or no, you can see it all here. Okay? This just helps you understand things a little easier. And the rest is just information for you. And the last bit of detail before I conclude is these two PDF files are not official documents. They are simply a summary of the SOP from Stago. So I did not prepare anything extra other than I took what's available in the SOP already, and I put it for you in a summarized form, that is, because definitely you cannot tell the customer every time they get MMin or MMax, oh, you have to go analyze from the IFU how the methodology works, then you have to go to the SOP. No one will ever do that, obviously, okay? So supply to the customer, no problem. However, make sure that the customer knows that the SOP is the reference document. This is not a reference document. This is not an official document. It's just a summary. The official document is the SOP in terms of the reporting limits, etc., etc., etc. Okay? From my side, I am done. So if you have any questions, please let me know. And again, this recording, I will keep it in the chat that's connected to this call. So you all have it easily afterwards. Just give me some time to upload the video. You should have it maybe in half an hour or so. So I am done. And if you have any questions, please let me know.
Thank you, Laith. Thank you so much.
You are very much welcome, Sally.
It's clear, Mr. Light. Thank you.
Perfect. You're welcome. You're welcome.